Okay, students, today we will discuss the radioactive decay process and its mathematics. Okay, so in order to better understand the radioactive decay process, first of all, we need to know what is meant by radiation. Okay, radiation. Radiation can be defined as means something which is coming out from any object that can be called as radiation, right? So some particles, right, coming out coming out from certain object, from certain object can be called as radiation, can be called as radiation. For example, for example, means if there is some, let's say, you can say there is an atom, let's say this is an atom, right? And I'm not showing here the nucleus and the electrons here. So you know that if let's say some photon is coming from interior of the photon, means sorry, from the interior of the atom, this photon will be a kind of radiation. Means you know that this is called as electromagnetic radiation. And similarly, for example, there is a nucleus, and from within the nucleus, you might get uh, a certain particle coming from inside of the nucleus. Let's say alpha particle, right? Alpha particle. Similarly, from within the, you can say from within the nucleus, you might be getting beta particle, right? Like from the nucleus, we might be getting certain beta particle. So this means here, you can say you will getting these particles from the interior of certain object. In the first case, the object is atom. In the second case is nucleus from where the alpha particle is coming out. And in third case, there is also a nucleus from there, from within which you can say we are getting beta particle outside. So here, you can say alpha, beta, and the photon are called the radiations. The photon are the radiated particles, means the radiations, because they are coming from the inside of atom and the two nuclei. Okay, so they are the radiations, right? Okay, now when certain radiation comes out, what happens to the original object? Means if the photon is coming out from this atom, what will happen to the atom after emitting this photon? And when the alpha particle is coming out from the nucleus, what will happen to the, you can say, nucleus after emission of alpha particle? And what will happen to this nucleus after emitting certain, let's say, beta particle, might be beta positive, might be beta negative. Okay, so every type of radiation, you can say, given out by a certain object, means will have certain effects upon the object which is, you can say, giving out that type of radiation. Okay, so we will see that in case of the photon coming out, the atom you will go from excited state to, you can say, the ground state, or from the high energy state to low energy state. And same is the case here. In case of when the alpha particle is coming out, of something will be happening inside the nucleus, right? And we know that alpha particle contains two protons and two neutrons. That's why inside the nucleus, the proton number will be decreased by 2, and the neutron number will also be decreased by 2. So that will affect actually that the atomic number will decrease by 2, and you can say the neutron number will also decrease by 2. So overall, the mass number will decrease by 4. And when the beta particle will be coming out, so inside the nucleus, either the proton will be converted into a neutron, or neutron will be converted into proton. Okay. Okay, so this is the concept of the radiation. It is not necessary that only the photon, alpha particle, and you can say the beta particles can come out from within, you can say, the objects like atom and the nuclei. Other than these particles, in certain ways, means in certain artificial manner, we can get, let's say, certain other types of radiation. Might be one proton coming out within the nucleus, one neutron coming outside from the nucleus, okay, and so on. So these are types of particles which will be coming from within, from, you can say, within certain object, that they can be termed as radiations. Okay. Okay. So here now we come to the effect of, you can say, emission of radiations. Okay. You must know that the radiation might be, you can say, first of all, normally by default we say that radiation is something which is coming from within a certain object, but the radiation might be being emitted, might be being absorbed. So there are two cases: the radiation might be being emitted, right, and might be being absorbed, right, absorbed. So in both cases, the object, you can say, will be affected. If the object is emitting radiation, and after emission of radiation, certain properties, certain aspects, you can say physical aspects of the object which is emitting radiations, the properties of that object will be affected. Okay, and if the radiation is being absorbed by a certain object, in that case, even then the properties, some physical aspects like let's say if a certain nucleus is absorbing, let's say, certain neutron, in that case, its neutron number will be increased. And if it is giving out neutron, its, you can say, neutron number will be decreased. Okay. So there are two cases here. In case of radiation, either the radiation might be emitted, might be absorbed. In both cases, the object is affected. Means object properties are changed. Properties, right? One or more than one properties might be changed, right? Are changed. Okay. Now we come to the radioactive decay process. Okay. Okay. Now the radioactive decay process. So this radioactive decay process, this topic also contains the word decay. So by decay, we mean to say decay. Okay, decay. What is meant by decay? So the word decay means, you can say, losing, when the object loses its identity by, you can say, normally by emitting the radiations. In that case, we say that that object is decaying. I mean, if the properties of that object are changed due to emission of radiation, that is normally said to be decaying. Okay, so means you can say by decay means say losing, you can say uh, losing identity. Okay, losing identity uh, uh, by an object, a particle, you can say, uh, through due to emission of radiation, due to emission of radiation, is called decay. Is called decay of that object. Okay. For example, if there is an object, for example, this is an object, right? And let's say this is giving out certain radiation. Okay, so that will change the object. Means now the object will be found to be with different properties as compared to its initial properties. So in that case, we will say that object has decayed. Decayed in what way? By emitting radiation. Okay, radiation. So we will say that object has decayed. Object has decayed, right? Right. Okay. Now we actually come to the radioactive decay process. Okay. Okay. Radioactive decay process. Okay. First of all, before we go into the detail of this process, we can define the radioactive substances. Okay. Radioactive objects are substances. Radioactive substances are objects, right? So how do we define the radioactive substances are radioactive objects? Those objects which can which can give out radiations, which can give out certain type of radiation, which can give out certain type of radiation are called radioactive substances. Radioactive substances. Okay, for example, the radioactive substances might be, you can say the photon emitters, or let's say the gamma emitters, right? Gamma is kind of, you can say, photon having much more energy, which comes a photon coming out from within the nucleus, that is called gamma particle. That radiation is called as gamma radiation. So gamma emitter means those radioactive substances which emit, you can say, gamma particles. They can be called as gamma emitters, and those particles which are those objects which emit, you can say, alpha particle, they can be called as alpha emitters. Alpha emitters. Alpha emitters, and you can say no doubt the beta emitters, etc. Right? So these are the examples of radioactive substances. Okay. So if the substances are the nuclei, and the nuclei, some nuclei might be gamma emitters, good gamma emitters, some might be good alpha emitters, might be good can say beta emitters. Okay, so by the radioactive substances, we mean to say the objects, the particles which can give out, you can say, certain type of radiations, and due to the emission of the radiations, they can lose their identities. They can lose their means the, you can say, the properties. Okay, by emission of the radiation. Okay, now now we come to the radioactive decay process. Means we come to the process in which unstable nuclei, you can say, emit certain types of radiations, and after emission of those radiations, the nuclei lose their identity. Means they are transformed from one kind of nuclei to other types of nuclei. Okay, so in that case, uh, it is you can say it is formulated that the rate of decrease of decaying nuclei is proportional to the number of radioactive nuclei present at any time t. So mathematically, this proportionality can be written as uh, dn over dt proportional to minus n, right? So here dn over dt is you can say the rate of decrease, right? Rate of decrease of what do you say? Rate of decrease of radioactive nuclei, radioactive nuclei, right? Because here we are saying that this is rate of decrease, because due to negative sign we are saying that this is a rate of decrease. So here negative sign is indicating that the radioactive nuclei will be decreasing with the passage of time, and this rate dn over dt is proportional to the number of radioactive nuclei present at any time t. Means here this n is a number of uh, undecayed uh, radioactive nuclei. Means the number of undecayed radioactive nuclei at any time t, at any time t, right? Okay, because means this means that n is a function of time t, because this n will be decreasing with the passage of time. So that's why this n, capital N, the number of radioactive nuclei, will be function of time. Okay, so here this proportionality sign means can be, you can say, removed, can be finished by involving a constant of proportionality. Okay, so this equation means we will get dn over dt equals, let's say, certain constant of proportionality. So that constant of proportionality can be named as, let's say, lambda, okay, and into capital N. So this way we will be getting here an equation, a differential equation, right? This is a differential equation, right? This is a differential equation because this is involving a derivative of capital N with respect to time t. Okay, so this is you can say this is a differential form of, this is a differential form of law of radioactive decay process, law of radioactive process, radioactive process. Okay, and here lambda is the proportionality constant. Okay, in the next steps we will come across the definition of lambda. Okay. Okay, now here dn over dt is equal to minus lambda n, right? So here keep in mind lambda is actually, you can say from here lambda will be coming to be equal to minus dn over dt by capital N, means it's absolute, right? Means in order to ensure, we are taking here the modulus in order to ensure that this constant of proportionality lambda comes to be positive, definite, means there is no chance of lambda to be, you can say, negative. Okay, and this can be defined as, this is actually you can say the rate of decrease, rate of you can say decrease of you can say an per unit available number of nuclei, right? Means those nuclei which are available which have not yet decayed. Okay, uh, or you can say that this is a rate of decrease, means decay of decay or decrease of number of uh, radioactive nuclei per unit time, per unit time out of available radioactive nuclei which have not decayed yet, right? So this is that is, and this keep in mind here that this lambda with the passage of time will remain constant. So that's why this is called as proportionality constant, because dn over dt, you can say, because with the passage of time capital N will be decreasing. So when capital N will be decreasing, and we know that dn over dt is you can say proportional to minus n. So if n is decreasing, this dn over dt will also be decreasing in such a way that their ratio remains constant. Okay, so that's why the lambda is called as a constant of proportionality, and it is specially named as decay constant. Decay constant. Decay constant. It is named as decay constant because this constant of proportionality is a constant value. It remains constant during the decay process. So that's why the word decay is attached, means it is called as decay constant. Okay. Okay. So we come to the units of, now we come to the units of this, you can say, the constant of proportionality called lambda. Okay. What will the units of, units of lambda? What are those? We know that this is dn by dt over capital N, and n means they have no units, they are just numbers, and this is dn over dt. So the units of lambda come to be, let's say, second are the time units, right? So this will be in seconds, or in you can say minutes or hours or milliseconds or microseconds and so on. So it means this capital lambda, this capital lambda will be having the units of seconds minus 1, means 1 over second, sorry. So its dimension will be of the dimension of 1 over time. So the dimension of lambda is 1 over time. The dimension of 1 over time is the dimension of lambda. Okay. From here we move onward. Okay. Okay. So one thing is important here that if there are many large number of radioactive nuclei, so every nuclei will be, you can say, decaying randomly and spontaneously. Means this decay process, the radioactive decay process, will be totally random and spontaneous. So note that radioactive decay process, radioactive decay process is a totally random and spontaneous. Random means any nucleus can decay at any time. We cannot predict that which one nuclei will decay at what time. And spontaneous means that the external factors like pressure, temperature, or any other external aspects cannot force the nuclei to decay, right? At a certain, you can say, instant, the external factors cannot force the sample nuclei to decay in a particular way. So that is called as spontaneous, means the nuclei will be decaying on their own, means we cannot fix them. We cannot we cannot, you can say, specify the style of their radioactive decay. That is called as spontaneous. Okay, so this means the random nature of the radioactive decay means that every you can say nucleus will be having you can say different nuclei will be having different lifetimes, means they will be decaying at different time values. Okay, so that's why their lifetimes, you can say, will be differing from each other. This means uh, the lifetimes the lifetimes of different different radioactive radioactive nuclei will be different or will be random due to their random decays. Okay, that means if let's say there are 1000 you can say nuclei, then each of the 1000 radioactive nuclei, each nucleus will be having its own lifetime, means different nuclei will be having different lifetimes. So if the lifetimes are different from each other, we can estimate and you can say an average lifetime that can be obtained like this. Let's say average lifetime that can be found out, and that can be called as, let's say, tau, and tau, let's say, average, right? This can be means obtained by tau 1 plus tau 2 plus up to so on, let's say tau n over, and how many nuclei, let's say in this case we are taking here, there are total n, small n number of nuclei, so that's why here means if we take it, let's say n naught, means there are n naught. N naught stands for the originally present number of radioactive nuclei. So that's why we will be summing up. We will summing up the lifetimes of all the radioactive nuclei if all of them have decayed. So in that case, we will be dividing with the total number of nuclei initially present. In that case, we will be getting the average lifetime of the nuclei. This is a collective value which will be representing, you can say, the average lifetime of the radioactive nuclei, radioactive sample. Okay, so interesting thing is that you can say lambda value helps. Lambda value helps to find you can say the tau average, right? That is 1 over lambda, right? So 1 over lambda here will be actually the average lifetime of the radioactive sample whose radioactive decays are being studied. Okay, so here in case of radioactive decay process, the proportionality constant lambda will be actually equal to the reciprocal, the inverse of the average lifetime, or the average lifetime will be equal to, you can say, 1 over lambda. Okay, so in place of lambda, we can put 1 over tau average, or 1 over, you can say, the average lifetime in the differential equation. In that case, the differential equation will be involving the average lifetime. Like your differential equation dn by dt, which is equal to minus lambda n, that is by put lambda to be equal to 1 over tau average. So in that case, this will give us dn over dt equals minus 1 over tau average times capital N. Okay, so this is the differential equation, or this is the differential form of the law of radioactive decay, in which instead of the proportionality constant lambda, we are taking tau average, which is the average lifetime. Okay, so this is you can say again the differential form of differential form of law of radioactive decay process, or the law of radioactive decay. Okay, so in the next lectures, we will come across, we will discuss the possible, you can say, solutions of the differential equation representing the process of radioactive decay. Okay, thank you.